A very good morning to all of you. Today I'm going to show how to evaluate the flux integral using divergence theorem in Maple software. Okay. As usual, we press the restart to clear the previous memory. Okay. The problem is, the example, use the divergence theorem to evaluate the outward flux of vector field fxyz is equal to z squared I plus xj minus 3zk across the sphere x squared plus y squared plus z squared equal to 4. Okay, as you have learned, the flux is actually given by surface integral f dot n d. The s here is a 1 unit of surface area of the surface sphere, okay, which is radius 2 units centered at origin. Okay, if you're not using the divergence theorem, since sphere you have a two different unit vector. If upper hemisphere unit vector n is pointing up, while the lower hemisphere unit vector is pointing down. So in this case, you have to break the surface S into S1, which is upper hemisphere, and lower hemisphere, which is S2. Then you have to evaluate your flux integral through time. However, if the surface is closed and the flux is outward, then you can use the divergence theorem, which says that the surface integral of vector field is equivalent to triple integral divergence of f, which is given by del dot f dv. Okay, because the surface is closed, it forms a solid G. So instead of you evaluate the flux integral, you evaluate the triple integral, where the integrand is actually divergence of f, which is del dot f dv across the solid G. So to evaluate the divergence of f here, we call the vector calculus package, where in the vector calculus package here, I'm going to use this divergence function to evaluate del dot f by calling this divergence function. Okay, and then I call the plots because I'm going to plot the vector field in 3D for you to see, which is where is it? Field plot FFF. Okay, I'm going to call field plot 3D. Okay, to plot the 3D vector field, okay, for you to view. Okay, and as you know, okay, you can press this one to execute the whole worksheets, entire worksheet. Okay, or you may press the statement line by line. Then we set the coordinates, okay, the Cartesian coordinate x, y, z. Defines the vector field f. Okay, this is define it using the functions ways, okay, under the expression using this one. By the AB, you change it to xy and then add in a comma and z. So the z here, put it to vector field. Okay, we're going to define the vector field. Component I is actually given by the question, which is z squared. Component j is x. Component k is negative 3z. So this component j, this is a component k, negative 3z. So multiplication, make sure you have a dot here. It stands for multiplication. To get this one, press Shift 8. Okay, and then we call back fxyz. So z squared. Ex is actually unit vector in Cartesian in x-axis, or in mathematics we put it in I. Ey is actually the j unit vector in the y-axis. Ez is a unit vector in the z-axis. In mathematics, Ex is an I, Ey is a j, Ez is a k. So this is to show back whether we define the f correctly. And then when you call the field plot 3D, since the vector f is 3D, so we call field plot 3D. If vector f is 2D, you just call field plot only. So it gives you the direction of the vector field, okay, f in 3D, because f is 3 dimensions. You can rotate and have a look there. This is a field plot 3D. And calling the divergence under the vector calculus package, you get the answer is 3. Okay, you may evaluate it manually. Del dot f is actually del del f mean del is a differential operator, del del xi plus del del yj plus del del zk dot. So means I will dot with ij, with dot with jk, dot with k, we get 1. So means it's actually component I is del del x. So you del del x, z squared, you have 0. For component j, you del del y x, you get 0. Component k, you del del z, negative 3z, your answer is negative 3, which is correct. In Maple, straight away, one command divergence f, you get the answer is negative 3. So now we are going to evaluate. We already obtained the divergence of f, which is negative 3. Now we are going to evaluate the triple integral dv, where the integrand is actually the result of divergence of f, which is negative 3 dv. Since the solid is a sphere, so we can use a spherical coordinates, where spherical coordinate we change it to rho squared sin phi d rho d phi d theta. This one that should so to delete, just control delete. In the plug is actually given by the triple integral. Call back the divergence fx y z dv, because the sphere is a the solid surface is a sphere, it forms a solid given by sphere. Then it will be easier, we use spherical coordinate. dv, change it to rho squared. How you get the rho is from the Greek symbol. To type the squared, mean the superscript, press your shift 6 will go up. Means I may show you. Yeah. Let's see. Go down here. F here, that should rho squared, rho squared sin phi. Rho and then squared. Left key to move down, rho squared times sin phi. Phi is here, rho squared sin phi, and then you want d rho, d phi, d theta. Limit of rho. Sin is a sphere with radius 2 units, so 0 to 2. Phi, sin is a full sphere. Phi, you measure it from the top surface of your sphere, which is 0, until the bottom surface, which is pi. Theta, you rotate it horizontally across your sphere, which is one cycle, 0 to 2 pi. So 2 multiplied shift 8 and then the undo. Yeah. 0 2 times the pi getting from Greek here. And you have this one, divergence. Answer is negative 32 pi. If you want to assign to a variable, then you so negative 32 pi assign now to the flux. So the result using Maple is negative 32 pi. If you evaluate it manually, you will get the same answer here. So here I revise back, I conclude back how to use Maple to evaluate divergence theorem. So the divergence of f, you just call. Make sure you turn on the vector calculus package and call the divergence, the function divergence. And then put it here, divergence. And then dv depends on the solid that you obtain. In this case, it's sphere, so we use spherical coordinates. So rho squared sin phi d rho d phi d theta. The sphere with radius 2 units, so rho 0 to 2. Full sphere phi from 0 to pi, theta from 0 to 2 pi. The field plot 3D for you to view the direction of the vector field. This one is calling back the function to see whether you define it correctly. So this is a vector field f. For other vector field f, you just change component I, j, k in here correspondingly. Okay, make sure you set coordinate, callings with plots, okay, with vector calculus. Okay, with this, thank you for your attention.